we did MA1 and we saw it is not as easy or straightforward as an AR model because of random components. And soon you will see MA2 just makes it harder, and if we go to MAQ, it just gets harder and harder. MA2 xt equals 80 minus theta 1 a sub t minus 1 minus theta 2 a sub t minus 2. Theta 1, theta 2 are the coefficients, and what is the characteristic polynomial? If we write it in terms of backwards operator, this would be theta 1 b times at a sub t minus theta 2 b squared a sub t. A sub t is in common. 1 minus theta 1 b minus theta 2 b squared. That is theta of b. If we convert this to an AR infinity, in other words, if it ends up being invertible, then we would have pi of b to be 1 over theta of b. So when we divide, turn it into an AR infinity, the weights that you get there would be pi values, provided the model is invertible. Well, what is the condition for invertibility? It's very similar to AR. The root of that characteristic polynomial has to lie outside the unit circle. There is no point whatsoever in converting or rewriting in terms of n forward difference. There is nothing forward about noise. It has to go only backwards. So along the same lines of going backwards, we started with gamma sub h. Covariance xt, comma, xt minus h, with AR, where they use minus h to derive, plus h to derive, you are going to have no problem. But here, it's more of an intuitive thing. There is no point in moving forward. Let's start with 0. Gamma 0 is easy. Covariance of xt, comma, xt. And if I rewrite, I'll simply have 80 minus theta 1, 80 minus 1, minus theta 2, 80 minus 2, comma, 80 minus theta 1, 80 minus 1, minus theta 2, 80 minus 2. Covariance of xt, comma, xt is nothing but the variance. And do keep in mind the variance of 80 is not the same as the variance of the series. What we're trying to find is the variance of the series. I don't know why I'm in the 80 kind of mood today. Maybe because did I use epsilon t or at in my derivation for derivatives. Something I even specify. Regardless, I'm not an epsilon kind of weird. So 80, what is the covariance of that? It is the variance, but what would it be? Should we change it to epsilon? So what is the answer? Sigma squared of A. So this would simply be the variance of noise. And variance of noise is nothing but sigma squared A. So that would be sigma squared A, great. This and that. The variance of 80 noise component at time t, would it have anything to do with noise component at time t minus 1? No. So covariance of this and that term will be 0. So plus 0 or minus 0. What about 80 and 80 minus 2? Do you think that they would be related? No. So that's gone. What about 80 minus 1 and 80? We've already established that. 0. What about 80 minus 1 and 80 minus 1? The random component at time t minus 1 is definitely correlated with itself. So here I have both covariance of negative theta 1, 80 minus 1, negative theta 1, 80 minus 1. That term and 80 minus 2, no correlation. So the random component at t minus 1 is not correlated with the random component at t minus 2, so 0. I guess combine all the zeros and put a big 0 here.
Why don't we switch from minus to plus?
Here, doesn't matter.
Well, yeah, for covariance.
Oh, but there's a reason, we'll get to that. I took the minuses that are right here, and I put it inside.
Okay.
There's a reason. I'll get to it. Line 8 is 2, and 80 minus 2, 80 minus 1, no connection, still 0. What about 80 minus 2 and 80 minus 2? Would they be correlated? Yes? Okay, so that term will survive. So negative theta 2, 80 minus 2, comma, negative theta, oops. No, oops. Okay, that is sigma squared A. Long time ago, properties of covariance. If you have A times X, B times Y, you can pull the A out, you can pull the B out. So if I pull negative theta 1 out and another negative theta 1, negative theta 1 times negative theta 1 is, easy question. Theta 1 squared. Same logic over here. If I pull negative theta 2 out, negative theta 2 times negative theta 2, you will have theta 2 squared. we know already what those two are. Great. That is sigma squared sub A. So gamma naught is sigma squared A plus theta 1 squared, sigma squared A plus theta 2 squared, sigma squared A. What do we have in common? Sigma squared A. Good. Okay, so that is the variance of the series. We'll do one at a time. So one at a time in the sense, I will plug in h equals 1, h equals 2, and eventually when I extend it to NA cubed, so covariance of xt comma xt minus 1.
Not right now.
Covariance of xt is 18 minus theta 1, 18 minus 1 minus theta 2, 18 minus 2. 18 minus 1 minus theta 1. It is for t minus 1, so t minus 1 minus 1.
Hey, Toms.
A t minus. But that intention is based in two different colors, so you can see the difference. So whatever we did here to extend it to
So why did you write it? Matt, why does it start at 18 minus 1 instead of 18?
x t minus 1. Right, I'm shifting it by 1. So t becomes t minus 1, t minus 1 minus 1, t minus 2, t minus 1 minus 2, t minus 3. Okay, shift. Okay,
Would theta 1 of at minus 2 be the same as theta 1 of at minus 1? Or are those different values?
this one and that one.
The theta values, because the time is different. I was just curious.
So this theta and that theta,
Right,
they're the same.
okay. Even though it's at at minus 2, at minus 3.
Yeah, I mean, a regular AR model, does V1, V2 change when you change the time? No. There are cases where the parameter will change with respect to time, and that case would be a non-stationary model. So these theta values would end up being time dependent, so things would go back and forth. And
What happened?
they are just.
Okay.
That's not make everything best. We'll start with covariance of 80, 80 minus 1. Do you think that there would be a relation? No, so 0. Covariance of 80, 80 minus 2. Do you think there would be a relationship between the two? No, so 0. Covariance between 80 minus 1 and 80 minus 3. Any connection? No, 0. So all of them became 0. Off to the next step. Negative theta 1, 80 minus 1. Would it have any relationship between 80 minus 1? Yes, so keep that term. Negative theta 1, 80 minus 1, negative theta 1, 80 minus 2. Do you believe that there would be a connection, correlation? No, 0. What about 80 minus 1 and 80 minus 3? No connection, gone. What about covariance between 80 minus 2 and 80 minus 1? Nothing. What about 80 minus 2 and 80 minus 3? Yes, so keep that one. Last but not least, covariance between 80 minus 2 and 80 minus 3.
Yeah, that's all I know.
Theta 1 outside with negative, it would become negative theta 1, covariance 80 minus 1, comma 80 minus 1. Negative theta 1 comes out, negative theta 2 comes out, so you have theta 1, theta 2, covariance 80 minus 2, comma 80 minus 2. What is that? If
Sigma squared, so that.
sigma squared A, it is the variance of 80 minus 1, that is the variance of 80 minus 2. Well, checkpoint. Let's see who remembers stuff. Why did we maintain this value to be the same as that value to be the same as that value?
Because noise is independent and identically distributed.
Very good, Joe. Because noise, our assumption, is independent and identically distributed. So negative theta 1, sigma squared A, plus theta 1, theta 2, sigma squared A. What do we have in common? Sigma squared A. If I pull that out, negative theta 1 plus theta 1, theta 2, sigma squared A. Off to gamma 2, covariance xt, comma xt minus 2. Xt is simply 80 minus theta 1, 80 minus 1, minus theta 2, 80 minus 2, comma. Shift by 2 backwards, a t minus 2 minus theta 1, a t minus 3 minus theta 2, a t minus 4. Give you a catch up. Designating the covariance, do we expect a correlation or relationship between 80 and 80 minus 2? No, so disregard. 80 and 80 minus 3. Connection, no. 80 and 80 minus 4. No. 80 minus 1 and 80 minus 2. No connection. T minus 1, T minus 3. No connection. T minus 1, T minus 4. No connection. Roll 0. Before we proceed, can we do the same thing with AR? An autoregressive model they keep dropping like flies here, but Joe says we can't do that with AR. Why not, Joe?
Because each term is, regress off of itself. So
Exactly, so if I have an AR2, XD depends on XD minus 1, XD minus 2, which would simply mean if I did a shift and wrote it as XD minus 1, it has to depend on XD minus 2, XD minus 3. XD minus 2 will end up depending on XD minus 3 and XD minus 4. So it is autoregressive, it has to depend on itself, so there we can't do this. I'm able to do this because that and that both have some random components, and they will have no connection whatsoever because they are independent of each other. Okay, I believe I'm at that turn now. Any connection between this one and that one?
yes,
Yes. Connection between 18 minus 2 and 18 minus 3. No correlation, 0. 18 minus 2, 18 minus 4. No correlation, 0. We have a negative theta 2, so we can pull that out. And that would end up giving negative theta 2 for gamma 2.
What happens with the sigma squared A?
Oh, my brain's going thinking of root. So, sigma squared. Good. With MA1, where did we stop? The gammas.
Technically after gamma one,
Oh, what?
technically after gamma one.
We stopped technically after gamma 1.
yeah, because gamma 2 equals 0.
Gamma 2 is 0. What about gamma 3?
It's also 0.
Andres, you were about to say something. Same?
Yeah.
Okay. So they're all 0 past gamma 1. So same logic here. Past MA, for an MA2 model, past time step 2, theoretically speaking, gamma 2 would be 0. In practice though, it is not going to be exactly 0, but it will fall between those two blue dotted lines that I showed. We will go back to that soon. So we have gamma naught, we have gamma 1, we have gamma 2, and gamma h is 0 theoretically, or h greater than 2. In a way, you can show that it is 0, because if you have 80, 80 minus 1, 80 minus 2, shifted one more time, the starting point here would be t minus 3, right? Those will have nothing to do with t minus 1, t minus 3, t minus 4, t minus 1. Not going to happen. So, how do we find rows? Row 0, row 1, the races?
every page shows it in the.
Very good. The auto correlation row H is simply gamma H over gamma naught. The variance or covariance of lag H divided by the variance of the series. So row 0 is always 1 in a class. Hopefully, row 1 is gamma 1 over gamma naught. Well, what is gamma 1 negative theta plus theta 1 theta 2 times sigma squared A over 1 plus theta 1 squared plus theta 2 squared times sigma squared A. Sigma squared would go away. Negative theta 1 plus theta 1 theta 2 divided by 1 plus theta 1 squared plus theta 2 squared. Row 2 would be gamma 2 over gamma naught. Gamma 2 is negative theta 2 divided by 1 plus theta 1 squared, theta 2 squared. We have sigma squared A term, which is going to get cancelled. So we will simply have negative theta 2 divided by 1 plus theta 1 squared plus theta 2 squared. Good. Last time I made a comment, unlike AR, the equations that we will get here in terms of thetas are not linear. So if you go back and look past the expression for gamma naught in an AR series, the denominator was simply 1 minus B1 minus B2 and so on. In other words, you have linear factors. Here, it's not linear. You have theta 1 squared, theta 2 squared. Making things worse, where you have theta 1 times theta 2. So it is no longer a linear system. Makes it a pain to solve.
Oh,
The cube over there earlier, it is true. Again, my brain is going ahead of me. Questions so far? Are we good? We saw last time with MA1, we were able to estimate the values of theta 1 and theta 2, but, theta 1, but it ended up being imaginary. The only way we can say that we'll get a proper group, in other words, a proper coefficient, is when some conditions are met. What was that condition last time? We set the discriminant to be greater than or equal to 0, obtain the condition for row 1. Same applies here. Row 1, row 2 must satisfy certain conditions for us to even bother estimating the values of theta 1 and theta 2. So going back, conditions. 1, invertible. They've addressed that already, the roots of the characteristic polynomial. One more time, must lie outside the unit cell. Erase. Instead of getting to an example, then coming to a condition, let's go ahead and look at the condition. So this is a quadratic equation, do we agree? And I'm going to rewrite it this way.
Hey, how are you?
Good. Root of b would simply be another time minus b minus of minus theta 1 plus theta 1 plus or minus square root theta 1 squared minus 4 times a times c. Divided by 2a, which is 2 times negative theta 2.
Ugh.
And that's what we will have. Well, I have the roots, and the roots of that equation, they are in terms of theta, right? That is useless to us. Why?
Trying to estimate.
We're trying to estimate it. How would we be able to come up with a condition if what you're trying to estimate is the condition, right? So we've got to rewrite it in terms of the rows. That's exactly what we did last time. Row 1 had to follow condition that it is less than or equal to 0.4. Yes, same logic here. I'll leave that row 2. Row 1.
Oh. Oh.
Well, a couple of ways in which we can obtain a condition. If I divide those two, what will I get? Row 2 over row 1. According to the characteristic polynomial, I want theta 1 squared plus 4 theta 2 to be greater than or equal to 0. to get there, I've got to do some kind of magic here. So if I divide the two, what will I get?
Row 2 over row 1. Should get theta 2 over negative theta 1 plus theta 1, theta 2.
Yes, the denominators will simply get cancelled. Well, row 2 times that will be negative row 1 plus theta 1, theta 2 equals negative row 1, theta 2. Cross multiply. Negative theta 1 row 2 plus row 2 theta 1 theta 2 equals negative row 1 theta 2. How did I get to that set? I simply divided row 2 by row 1. Move that to the other side. So theta 2 row 1 plus row 2 theta 1 and theta 2 minus theta 1 equals 0. That is one equation. We need another equation, correct?